Hello everyone! We are the Terra Team Competition and we represent the Federal University of Santa Catarina in Brazil. In this video, we will present Alvide, an autonomous underwater vehicle that we developed over the last few months to participate in this edition of RoboSub, which is our first participation in this competition. Because of the COVID-19 pandemic, we had to adapt our activities so that the project could be carried out at a distance. So our results were all obtained through computer simulations.
For the structural modeling of our AUV, two possibilities were initially studied: create a new structure from scratch, or take advantage of the Blue Rock 2 design and make improvements to it. After discussions and studies by the team, the second option was chosen, due to the possibility that new solutions can be implemented and tested more easily for this case. With this, the team improved the vehicle's original design, adding a frame and a waterproof enclosure to it, providing more space for the allocation of components and thrusters. The material used in the frame was HDPE, which has resistance to high tensions and low density when compared to other materials. In the enclosure, the material used was cast acrylic, which has excellent resistance to mechanical stress and good thermal stability. The total weight of the AUV structure resulted in 17.11 kilograms, with 2.11 kilograms relative to the battery. The structural and hydrodynamic simulations were developed and validated based on a simplified geometry of the team's AUV.
A challenge faced by electronic systems is the heating of the components due to the increase in the intensity of electric current, resulting from the implementation of new functions and the simultaneous operation of subsystems. For our team, this challenge was reflected in the need for thermal control of a Raspberry processor, whose operation was critically deteriorating above 65 degrees Celsius, compromising the AUV's autonomy. In an initial state, the heat was dissipated into the air inside the enclosure and conducted through the walls to the external flow. The low thermal conductivity of the first 2 meters implied high thermal resistance, drastically reducing the efficiency of thermal control. The development of a solution was based, in synthesis, on the reduction of this thermal resistance. The proposition and evaluation of possible solutions indicate the design constraints and the preference to be met. They were the difficulty of repositioning the components, minimize the necessary changes imposed on the existing structure while preserving its integrity, minimize or eliminate required energy recruitment, and avoid configuration of devices that propagate electromagnetic noise that could interfere with sensor calibration. From these restrictions, the definitive solution found would consist of conducting heat through heat pipes to a heat sink installed through the enclosure wall. In order to prevent heat dissipation into the indoor air and the consequent reduction in the device's effectiveness, the entire surface of the device exposed to indoor air would be covered by an insulator. For a similar purpose, the contact resistance and the interfaces would be minimized through the use of thermal paste next to the processor and thermal epoxies on the mounting surfaces of the bases and heat pipes. The heat sink would be mounted through a single round hole and adhered to the enclosure wall via polymeric sealant before applying a primer, minimizing stress concentration and ensuring structural integrity and watertightness. For future projects, from the perspective of thermal control in the AUV, an interesting possibility to be addressed would be the reduction of the distance between the heat sources and the external flow, a quantity that generates the thermal resistance in the heat transmission between them.
The main challenge of the power system was to achieve a good autonomy for the vehicle, while maintaining the performance of the electronic components. The heart of the submarine inside the Alvide's enclosure is made up of the Raspberry Pixhawk NSX component. In the outside are the thrusters. To meet the different voltage requirement between components and thrusters, we use two batteries, The intention was to avoid overcharging a single battery and not need to implement voltage reducers, since the internal components need a lower voltage. We use Samsung cells to build batteries that fit the project and in another enclosure for the protection of the components.
The structural simulation were performed using ANSYS software to determine internal and external forces and the corresponding stresses, as well as the determination of displacements and corresponding deformations of the design structure, so that with the obtained results it was possible to understand if the structure would resist to all tensions that would act throughout the mission. It was determined as input parameters the mass of the structural part of the AUV, disregarding the batteries that were still in the selection process. HDPE material was applied to the frames and cast acrylic for the water tie housings. In addition, the team considered a pressure of 4 megapascals, which is considering the AUV acting in the deepest part of the pool available at the venue. Finally, the supports were evaluated on the sides of the structure. With the structural simulations performed, it was possible to analyze the deformation results as well as von Mises stress and equivalent elastic stress. The region of greatest stress in the structure is the main water tie housing that will house the electronic system. The results indicate that this component will suffer the greatest deformation and structural stress. However, all values found are within the limits allowed by the materials, taking into account also an appropriate safety factor. The behavior of fluids is not very intuitive, making it very difficult to predict its impact on projects. It is very common to conduct tests in water to understand the behavior of the vehicle in operation. However, due to the possibility of conducting experimental tests, the team also used ANSYS software to simulate the flow behavior and analyze the obtained results. For this simulation, water at a temperature of 20 Celsius was adopted, with a flow velocity of 3 knots and a pressure of 4 megapascals. As a result of the conducted simulations, it was possible to understand the speed, pressure, and drag force on the AUV hull. The maximum drag force applied on the AUV in the longitudinal direction is 101 newtons. From this result, the selection of the correct power supply voltage of the thrusters were possible and thus selected the battery configuration most suitable for the project.
For the development of LV code, we work with ROS since it has the most relevant in details documentation of establish the communication. Therefore, we begin your attempt to link ROS with gazebo and the image recognition, where we attain satisfactory results, both in the communication and in the simulation performance. For the image recognition, we chose OpenCV library which the implementation of the codes in Python. It operates by detecting the vertical bars present in the competition gate and the providence of the coordinate. The idea of the QC came from the need to ensure the data security. Once triggered, the system sends light signals in SOS, guaranteeing that it is safe to run on the equipment. Throughout the video we show number theoretical solution. Whether in the future we intention to improve and implement each one of the and all the 5 tests or solution or say war test. In the long run, besides encrypt this task, our LV incapable of executing, we want to create mechanical arm to pick up objects. Implement DVL to accurate measure or vehicle speed and, last but not least, add a pin sonar and to locate objects under the sub. Thank you all for your attention and